Okay. Pamela, can you hear me? Should I start?
Yes, please. That's okay. Thank you.
Great, thank you. Okay, so welcome everybody, and good afternoon from the UK Standard Time in whichever part of the world you are. This is the featured webinar session organized by the Digital Surface Manufacturing Network of the EPSRC. I am one of the co-directors of this DSM together with our leader, Professor Alan Matthews, who is also in attendance, with Professor Ash Tiwari and Professor Adrian Murphy as well there. And it is my great pleasure to have this opportunity to invite Dr. Faisal from Robert Gordon University to tell us today more about residual stress in coatings area, which critically is linked with our objective of investigating mechanical properties, particularly the modes of failure and delamination of the coatings attached to substrate materials, different substrate materials. It is also my pleasure to say that I've been knowing Dr. Faisal almost like for 10 years, a decade now, since I first met him at Heriot-Watt University. We both are alumni of the same university, and since then I've seen him growing and only growing. He went on to join Al Faisal University in Saudi Arabia, where he secured a number of research grants from Aramco, Saudi Aramco, which is a big agency in oil sector. And he has been working prolifically in many areas, ranging from coatings, acoustic emission, sensing, in-process sensing in particular, neutron diffraction, and so on, the techniques that he's going to cover today, and has critically cemented his position in this academic sector, in wherein we can only expect him to see some more and more big results coming from his lab in the time to come. So it is a great pleasure to have him here with us, and I'm looking forward to hear what he will share with us today. And on behalf of the DSM, Dr. Faisal, I hand over the platform to you now. So please take over and please give us some new insights.
Thank you, Dr. Saurav. Thank you very much for the introduction. Let me share my slide, then I can start.
Yes, we can see.
Right, so that's me, Nadimul Faisal, from Robert Gordon University in Aberdeen. Currently, I'm a reader in mechanical engineering. Focus area is micromechanics and surface engineering. So I was invited to do this presentation. I decided to present in one of the area which I work, which is to do with residual stress analysis of thermal spray coatings. Before that, I would like to introduce who we are. Robert Gordon University, it is up in Scotland in Aberdeen. We have got about 16,000 students, mix of undergraduate and postgraduate and many nationalities. In this presentation, I will be presenting, starting with some background about issues or challenges in strain measurements, especially in particular for thermal spray applications, and give you some hint about what analytically can be done. But most of the talk will be about neutron diffraction based residual stress measurement. And then some new work we have done recently, which is to do with diametral compression method. And historically, my thesis was on indentation, Vickers indentation or fracture mechanics, contact mechanics of thermal spray coatings. And toward the end, I'll be presenting some of the things which I think could be future direction in this domain. As Dr. Saurav introduced, I work on micromechanics, contact mechanics, mainly using sensors, in particular acoustic emission sensors. on thermal spray coatings, as well as on adhesively bonded joints, polymers, and very recently I started doing some work on geological porous material and natural formation, understanding the strain at low temperature, high temperature conditions. Right, so before that, I would like to acknowledge all of my partners, collaborators, colleagues, or sponsors. Here I've listed them who work in thermal spray coatings. So I'd like to acknowledge Professor Shrikant Joshi, who is available today this meeting, where I got a chance to work in India at ARCI. At that time, it was Surface Engineering Division. Currently, Professor Joshi is at University US in Sweden. And then my colleagues, Mr. D.S. Rao, KRC Somaraju, Dr. Shiv Kumar, and D.Sen. And then later on, I worked with Dr. Rehan Ahmad, Bob Rubin, and Ian Steele doing my thesis, where I spent 5 years about learning about thermal spray coating, wear and tear, in particular contact mechanics, using sensors. And that is where, toward the end of my thesis, I was introduced about residual stress. Before that, it was not a common terminology for me. So I got a chance to work a little bit with Dr. Brian Alcock on thermal spray monitoring using acoustic emission sensors. Later on, we used a number of times and still using a neutron beam source at STFC. There are a number of colleagues. In particular, I worked with Dr. Anna Paradoska, who is currently in Australia. And then Dr. Theo Gusen at Al Faisal University. We got opportunity to work with Saudi Aramco on a number of projects. In particular, I was involved on solid oxide fuel cell, thermally sprayed coatings for anode application, as well as wear resistant coatings. Later on, in collaboration with Dr. Saurabh, we worked a little bit on molecular dynamic simulation on thermal spray. And these days, for the last 7-8 years, I'm at RGU working with a number of colleagues and students, and as well as Dr. Saurabh and Professor Hari at South Bank and Cranfield. As well as there are some project going on with Dr. Tanveer Hussain and his team at the University of Nottingham. Right, so I'd like to start with the background in strain measurement. Talk about a basic thing, touching upon some of the basic thing. So let's see what happens in thermal spray. So to start with, we need to know why residual stress analysis is important. We don't want to go in detail, but just saying that adhesion, fatigue, and other tribological behavior, these are very important for such coatings or any material you want to. So residual stress is important. Now, in this presentation, I'll be talking about how to measure it. What are different techniques? So there are 3-4 techniques I have prepared. Right, so to start with, we know that in thermal spray, you've got particles at very high velocity and temperature, which interacts with the surface. Now, surface can be of various shape and size. Here, you can see in the screen, it is a thick sample or thick combination with thin sample. You can be spraying in the corners or bends, or you can be spraying on rollers. So in all these cases, the geometry, the shape of the substrate will have an impact on the strain which will build up during thermal spray. So there are a number of factors which can lead to net residual stress. These can be different thermal spray techniques, process parameters involved, as well as the temperature, rate of cooling between passes. If you're doing preheating or heating during means post-treatment heat treatment can be done. Service loading, shot pinning, as well as the coating material, substrate materials. All these will have an impact on the final coating manufactured. Right, so this is what happens. Now, if you see on the screen, the desirable shape and size is the one you are spraying on. But during this thermal spec process, something happened in very small scale. Some deformation will happen because of spraying high temperature. And then you end up getting a substrate or sample which has changed in few minutes or seconds. However, when you develop your process parameter, you assume a number of things. So you assume a substrate is constant. You've got particular properties. However, these things changes during thermal spec process. So most of the research and development work done are on flat test coupons. However, when you deploy in real life, they are not on flat substrate. It would have different geometry, shape, and size. And because of that, that leads to uneven residual stress buildup. And a lot of things are known if you're spraying on corners, bend curvatures, or grooves. And we know, from my experience, I know that residual stress is not a common testing protocols in industry, either because of lack of resources or expertise or maybe lack of interest. Right. So if we do a Google search looking for what sort of shape and size thermal spray coatings are done, we come across, if you just did with the ball wall thermal spray, you can see these examples where you've got different shape and size. So if it is different shape and size, the thermodynamics will change. And that is a problem here, because that determines the quality of coating. In particular, if you're dealing with coatings on ball wall, you would know these are very expensive set of coatings. And if it is not properly done, and if you operate these ball walls with little contact with the accessories or contacting surface around, it can scratch the surface, which can lead to permanent deformation, micro crack, a groove, and that can not be helpful. So then you have to replace the ball wall, or you have to replace the coating, and that is an expensive process. In UK, it can cost you many grands. Right, so to start with, but the residual stress, we all know residual stress are those internal stresses which exist in the material part without the application of any service or external load. And this can be induced during manufacturing process, and there can be stresses, I call it global stress or macro stresses, or it can be ingrained in grain level or atomic scale. A lot of work has been done in this area. There's a lot of literature available. I would like to read this article, the original source of these definitions. As well as if you want to know much more about residual stress, so there are a number of textbooks available. And the last 20 years, there's some standard being developed. You'll find, and there are other techniques, drilling and X-ray, but you will not find neutron diffraction-based standards, because it's still, it is in development stage. So if you are interested in these, maybe good starting point to know about residual stress methods. Right, so in thermal spray process, what happens when you powder particle or feedstock material is sprayed in an environment at very high velocity and temperature, which will propel through the environment, and particle will land on the substrate. So, and then layer by layer, you can build coating. So if you have a sprayed only a few particles on the substrate, you can see on in the image here, it is a grit blasted surface. What we did is try to spray and then see how it will go deep inside those blasted area, because that will form a mechanical interlocking, and that is what happens if you want to improve the coating adherence with the substrate. So this is what image we try to capture. Now, all these, the first layer is very important because that is interacting with a different material with different mechanical properties. So the adherence at that point of contact is very important. Now, as you manufacture the substrate, it will have an impact on the surface you produce. So grit blasting will change the surface properties. Some of the strain will change in very small scale, but it does have an impact. But these are necessary. If you don't do grit blasting or roughening of the surface, then the coating will not adhere. So these are the natural process we have to follow. And for different type of thermal spray techniques, we are not going into detail what techniques they are. So, but these are typical spray parameters which can be applied. One thing important here to think about is the cooling down, the quenching process, or splat forming process. It happens in few milli or microsecond. Right, so the examples of powder particles on the left side is before you spray, on the right side when it is going through a spray and before it lands. So I would say we collected some powder particle. You can see the surface is partially molten and few particles are joined up, and that will eventually land on the substrate and it will form a splat-like. So either it is a proper splat or it can disintegrate into smaller particles. So in the first layer, it will interact with the rough surface, and that is where the mechanical interlocking would happen. Right, so to understand about what happens theoretically, we did some work using molecular dynamics simulation technique. The first work we did with Dr. Saurabh, where we investigated copper powder particle on copper substrate. And a couple of years ago, we did a project with our group students, final year project students, where they did a simulation on multiple particle sprayed onto substrate. You can see as it is sprayed, the strain builds up. So based on the size of the particle, you can see some of the features in it. Here on the right side, the particle size was large enough. You can see how the strain forms and where it forms. So these are important things to look into if you are thinking about developing coating of very small size. And as well as if you can work out for one layer, you can have multiple particle, large particle sprayed, and you can get the strain particle by particle or layer by layer. So these are some of the recent work. We know that there are about 10, 15, I would say in total publication in this area where molecular dynamics has been investigated for thermal spray application. So there's a lot of scope in this area. Now, this is an image of alumina powder particle sprayed using two techniques. The left side is the HVOF technique. You can see the initial powder, it is angular. The right side, it is a plasma spray. Both looks very similar, but you can see that the thickness are different for these and the size of these splat as well. Now think about these are and some of the unmolten particle a lot of porosity. There are gaps between splats. And alumina, you know, this is a very brittle material. Now think about that these are getting sprayed layer by layer. These are not so uniform. The splats are not so uniform, but there are some patterns you can see. So these would have a huge strain because these are sprayed at very high temperature. So the strain will be significant. Assume you're using this coating for some tribological loading or application. Assume you're applying some load on the surface. So because this is a brittle material, the load will not transmit to the next splat. So it will apply load and it will crack. So whatever you observe, you will be observing the failure on the surface, on the top few splats layers, and because the load transmission may not be so easy. So you may not get a proper tribological properties of the coating, thick coating itself. It will be mainly surface properties. However, if you're using different type of material which has got some ductility as well, so the loading load transmission will be different, so tribological properties will be different. Now, with these inbuilt residual stress, that will have an impact on overall failure of the coating. Right, so in thermal spray, there are some factors because of that there are residual stress which builds up, and those four few I would say: the quenching stress, and the pinning effect, and the deposition temperature, and the phase difference. So each of these combination of these will have an impact on the residual stress buildup. So assume you have got a single particle landing on the substrate. Because of high velocity, you're likely to see a little deformation, plastic deformation or elastic deformation, both could happen. The particle will become flat, and then the particle will have a quenching stress. At the same time, the phase transformation could happen. That can lead to a volume change. As soon as the volume change happens, so the strain will build up. And then based on the velocity and temperature, the local bonding will happen with the substrate. So this is a lot of events are happening in this small volume, and that is very important. That a lot of data is getting generated. And then if you build up layer by layer, powder particle, so you can end up getting a thick coating, and then eventually you will get a macro residual stress. Right, so that is a bit complex. If you keep spraying layer by layer, in the first layer, means within first layer, you would have sprayed the first few powder particles would have been sprayed on the substrate. And I've just described what could happen. Assume you are building a single layer, a thick coating, and then you have got a number of layers. Now, as soon as you spray on the second layer on top of the first layer, the substrate material has changed. The temperature has changed. The substrate has become thicker. So as a function of time, or as a function of a spray passes, the properties of the substrate is changing. Now, I've shown you an example before that with different geometry, shape, and size, things have different thermomechanical properties. Now, we develop some of the process parameter based on a typical, say, steel or titanium alloy or whatever substrate you are. You are not designing your process parameter for a new layer which has got new properties. So that is what happens in real life. But if you look into the physics of it, that changes. Right, so come to the residual stress method now. there are a number of methods, and those in blue color here, that is what I'll be talking in next few slides. A coefficient of thermal expansion, linear elastic, neutron diffraction, and a little bit on indentation and diametral compression. Now, each of these methods comes with a lot of advantage and disadvantage. So the main thing to worry about is how deep you can measure inside the coating and what is the resolution of it. So very briefly on analytical method, this is based on, there are a number of methods in this, but I've just selected one example, which is a coefficient of thermal expansion model. Now, I've taken these concepts from thin film because one of the area of work is on thin film, which is like DLC or titanium nitride or smart shape memory or alloy thin film. So here, what happens, you've got a substrate, you're depositing. So if you have got a compressive stress, so that is how it will look like. If you have got a tensile stress, then it will try to buckle off. Now, this image you can see, showing you just to compare this with this example, that you've got thin diamond-like carbon coating, which is normally would have large compressive residual stress. And as soon as you apply any load on top of surface, in this case, we applied a cyclic load, cyclic nano indentation using conical indenter. You can see after a number of cycles, the coating was buckling away from the substrate and leading to the cracks you can see here. So that is the mechanism of failure in thin film. I've never seen such failure in thermally sprayed coatings, largely because it is thick, it will have a different load distribution, strain distribution, and such loading environment. But that is a likely mechanism of failure. Right, so in all these cases, the number of mechanics is involved, and that is something to look into. Now, if you're looking into two-layer system, analytical model, coefficient of thermal expansion model, it is mainly to do with coefficient of thermal expansion coefficient. And you assume that those properties are constant. You assume it's got one elastic modulus, Poisson ratio, and you use this model to calculate, to have an assessment of what could be the likely strain or a stress. But it is very far off from the reality. So here we did some analysis on multi-phase material. You can see it was a mix of molybdenum carbide with alumina on histolite substrate. Here we selected some of the properties or measured some of the properties, some data coming from literature, Poisson ratio, and the thickness was the final thickness. And we selected the coefficient using literature value. For some of the material you may find, you may not find, so you can find some of the property, or you can come up with a property which is as close as possible. So you calculate the thermal stress, and you can see these values are very high in megapascal. Later on, I'll show you that the experimental values will be about 10 times lower than these. So in my opinion, doing analytical calculation is good to understand, but it is not a very real value. It may be useful for some other technique for thermal spray. I don't think so it is so helpful. Because if you do layer by layer, the dynamics, the strain which builds up in the substrate, it will change because the neutral axis with the thickness will be shifted. For single layer, neutral axis will be somewhere here, but if you build up another layer, the neutral axis will shift. And then that can lead to a bending into the sample. It depends on tensile or compressive residual stress. Right, so there are challenges So that's what we've got number of techniques. So let's start neutron diffraction. So recently we did a review on what are different diffractometers available worldwide. So these are in different continents. The most frequently used sources are ICE's Rutherford Lab, and another one is Australian Nuclear Science Technology Organization. So are these two labs, what we have seen, they are the frequent there are frequent users of these facilities for thermal spray coatings, where they can investigate the strains. So the strain is one thing they can measure, but there are many other things which can be measured, which I characterize as a microstructure. So maybe texture, phases, lattice parameters, pores, cracks, anisotropy, or maybe chemical impurity, dislocation. All these things can be investigated using neutron beams. Now, there are two different types of beams. Either it can be monochromatic or time of flight. So monochromatic source can do single phase. However, time of flight can do a dual phase like steel or other materials. So the one I use is ISIS one. It can do, it is time of flight based. So you can have a multi-phase coating material or substrate which can be investigated. So the manuscript is under review. However, you can see the preprint available online. Right, so what happens, these facilities are not available right away. You have to apply for beam time through proposals. If your investigation is innovative, you may get beam time, because these are very expensive experiments. So it requires a lot of preparation. As well as we need to know about the basic crystal properties, crystal systems, because as soon as you're dealing with any neutron or synchrotron or X-ray, these things communicate with crystals. So we need to know what crystal system your material is. A basic one, you don't have to go too deep, at least what crystal system is, cubic, hexagonal, monoclinic, or so on, because that can help you to analyze the data. And then a little bit more about learning the planes, crystallographic planes, because in these diffraction methods, you measure the D spacing and change in the D spacing. So you need to know the Miller indices, and there are some reading material I have listed here, which can be very handy. So if you are spraying, you're manufacturing coating, you would know what is your feedstock material, so you can do some basic characterization to work out how the crystal looks like, what they are. All right, so how the neutron works. Neutron is neutral. It is different than X-ray. X-ray has got negatively charged. If you're using X-ray on materials, so it will interact with your atom. An atom would have electrons. So X-ray negatively charged, electronically charged, it doesn't allow to penetrate into the sample. However, neutron, it is neutron, it is neutral. It can penetrate deep inside into the material. So that's the advantage, that you can read the strain inside the volume, which is not possible using using X-ray method. You can use to an extent a synchrotron, but in my opinion, neutron can give you much better results. Well, that is expensive, but the methodology is very similar, what you do in X-ray. The fundamental is same. You can use this geometry or Bragg scattering geometry. And one thing you have to think about is your time peaks are measured at time. So what is the time? So you can use these DHKL, mass of neutron, length of the flight path, and theta HKL, and H is the Planck's constant. So these things can help you to get us started with the measurement plan. Now, as soon as you do the scattering, you will come across a spectra like these, where you have got a d-spacing and x-axis, or time of flight, and then you get counts or intensity, and you get these peaks. You may have seen X-ray. In neutron, you also get similar peaks. So you need to know about each of those peaks, because you will be analyzing these in much detail. What you do in a strain, you measure the peak, and then you measure another location or another sample, another reference sample, and then you will observe some shift happening. So that shift, either this side or that side, that gives you the measure of a strain. So this equation you can see here, DHKL and D naught. D naught is a strain-free sample, D naught. So D naught is important here. Based on D naught, you will know what is your strain. If your selection of the D naught is not properly thought about, then you may get very high or very low strain. So what we did in our experiments, in different experiments, we took off the coating off from the substrate. We cross into powder form. That is one way. Or you can use before you spray your feedstock powder itself, you can use that as your sample for D naught measurement. For substrate, you can, So for substrate, suppose this is your substrate and you are spraying on top of it. So you can take this point as your D naught, or you can take an unsprayed substrate and measure D naught anywhere. So there are different ways to do it. For coating, you can take the coating off, you can crush it into powder and put into vanadium tube and get the D naught. So that is something you have to plan at the start before the start of the experiment. Now, a few details about the targeted, about the source itself. This one is based on tantalum target. It is based on time of flight. The resolution is 50 microstrain. If you have got samples less than 50 micron, I'm afraid this will be a challenging one. You can also apply fatigue loading on your samples. You can deploy different temperatures, cryogenic temperature, or furnace. You can have large samples, you can have small samples, or you can also do some scanning of the sample if you pinpoint which coordinate or which location of the sample you want to analyze. So these facilities can be accessed. Right, so in terms of measurement, in terms of preparation, this is a schematic diagram where you have got two banks, and the beam is coming from this direction. It is hitting the sample, and then beam will be diffracted. So there are two detectors. They will detect it, and then you can change the location of the sample to measure some other points. If you see the cross-section view here, what we are doing is measuring from top to bottom, or you can go from bottom to top. So you do point by point. You can do number of points in the coating and number of points in the substrate. So there are two banks. It means you will have data coming from both detector. Before that, you need to prepare, think about material you are going to investigate, because as soon as you do a diffraction, you will be getting a spectra, and you have to analyze some of the data right away. You have to think about the gauge volume and make sure the instrument is calibrated, and these things can be done by the instrument scientist available there. Right, so one of the things to worry about is the volume you are going to investigate. So assume this is your the coating, and that is your very thick substrate. So focus on the coating part. So if you have got a beam going to this space, this is a surface above, it is this open space. So you don't have to measure that bit, but you have to submerge the beam inside the coating. So how deep you should be. And you remember, these coatings are very thin. So 200 micron, 300 micron, these are typical thicknesses. So there are only a number of points you can analyze. So if you are too far closer to the top surface, so typically I would say go to 50 micron deep, and then you can, it depends if it is thick enough, you can have 4 or 5 data points from the coating, and then again you can do from substrate. Now the interface is important. If your points is here, you may get a lot of overlaps coming from coating and the substrate. If your points is here, you may get largely from coating and a little bit of substrate. So this is some of the thing to worry about at the start of experiment, because once you set the experiment, it will run for hours. And for coating part, it takes a lot of time. For these 4 or 5 points, you may end up spending 24 hours of continuous diffraction. However, for substrate, you can take a less number of time, maybe an hour or half an hour or so. Again, these decisions are taken based on the material. So in our cases, we typically take 3 to 4 hours per point to diffract and get a nice data, a useful data, I would say, for analysis. So before you set up all those things, you would like to do a fast scanning to find the reference point. Where is the interface? Where is the top surface? Where is the bottom surface of the substrate? So that you can write the code, how many data points you want to analyze in coating, how many in substrate, and then set up the time for each data point and let it run. Now, this is how you assemble your sample. You can just put in front of the slit. So this is the slit. Along deep inside, the beam is coming from to the sample. This is the top view. So think about this is a small test coupon. It can be large sample as well. You can put powder material in front of it, or you can put those powder material inside the vanadium can. Now, if the coating, if you're playing with the gauge volume, you may put some slit. And this is very useful slit for testing some of these coatings. This is just an aluminum plate which have got a very thin 0.2 mm wide slit in it. Right, so if you're analyzing your D naught for coating, you have to crush it as small as possible. We know that it can have some impact. It means you can introduce some shear into it. That is a possibility. Or you can use fresh raw material, raw powder for the purpose. Right, so once you have done that, then you have to do a number of analysis. So the number of analysis you can do average of all peaks, or you can analyze individual peaks. So if you've got number of peaks, it will be time consuming, but you can have a much detailed investigation. So there are softwares available for such purpose. And this is very data intensive. You have to do for each points, for each layer of means each levels for different HKL planes, and take the average. And again, you have to do for first bank, and then you have to do for another bank and take the average. And then if you've got number of samples, you can spend weeks and months analyzing all these data. Right, so the interface is an important thing to worry about. If you're analyzing within 50 micron on either side of the interface, you have to be very careful. You can expect huge error if you're not analyzing the data carefully. However, a lot of work which can be done in this domain, a large set of data of different types can be investigated. In my experience, I would say this is an area which has been very least investigated at the interface of these coatings. A very steep rise in residual strain grain can happen. Right, if you want to measure the stress, converting a strain into a stress, you have to measure the elastic modulus. In this case, what we did a cross section of the sample, and we did indentation testing on different points. So here is the scheme of those indentation point of the cross section. So either you take the elastic modulus value of the coating itself from some literature, or you measure it. If you want to measure it and do proper measurement and use that value to convert a strain into a stress, like we have done here, you can see that for the coating part, elastic modulus is not constant. It varies from level to level where you are. However, for the substrate part, you can see it is very similar. So this is one way you can use it. Or if you want to simplify it, you can just pick one value to convert into a stress. So these are some of the examples we have done on hydroxyapatite biomaterial, as well as alumina coating. And you can see here for one coating type, the strain is largely tensile. For another type, you can see you've got a lot of compressive strain. And we did indentation on those two samples. You can see the surface fracture is a bit different. So the high tensile residual stress here would have impacted the failure of this plasma sprayed alumina coating. However, for HVOF, the pattern is comparable to some of the standard fracture mechanics in indentation. There are very little work available where comparative analysis has been done. This is one of our examples where we have used a deep hole drilling method with neutron. You can see the limitation of neutron, the limitation of the deep hole drilling method, especially at the interface. So a lot of stress relaxation can happen as you drill, which is not which a drilling method cannot measure. So that is important. However, if you want to see additional details here, if you do hipping hip sample at 1200 degrees centigrade, you can see there are some stress relaxation has happened. So still, this is an area where I believe maybe in future, a lot of information can be obtained if we do comparative analysis. Moving on, this is a new method, I would say. The method is not new, the application is new. All right, so diametral compression method is used mainly in geomechanics to understand the tensile strength of geological samples. What we did in this case, we deployed a disk type sample. You can see here a substrate without coating, a substrate with coating. On one side it is coated, and you are applying a load on this. So this is a side view. If you see the front view, and we have what we did, we put a strain gauges into different direction, one direction and this direction, so that you can measure X and Y strain. And we applied a compressive load. Because of that, the coating came off, and before it came off, we measured some set of data about the strain. So you will find some fundamental theory, the theory involved, the equations involved. You can see all these strains in different directions. So here are some results. You can see that with the load, this is a load profile, and then these are the strains. Anything below 0, these are compressive. Anything above this is tensile mode. So you can see at the point where it is changing to nonlinear. This is the point where we compared with the substrate and the coating. So you can compare the strain data coming from substrate, strain data coming from coating and substrate, and see what are those values and take the difference of it. So you can have a relative strain mismatch, which can be investigated using this method. And this could be an alternative method if you compare with a standard adhesion method, which is used in thermal spray coating. And we compared these data with the neutron on the same material, and the results can be, it was way off because there are two different techniques, but it would make sense if we investigate more. So if you want to have a look, you can have a citation of this work. Then we did some stress analysis using finite element. You can see there's a huge mismatch in the substrate and coating side. So these are, so if you want to compare these two, this is on the coating side and the substrate side and so on. So you will find that once you compress the coating surface and the substrate surface and the interface on the coating side and the substrate side, they would have different strain or a stress distribution. So these would have an impact on the overall quality of the coating. So we think that this can be an alternative way to measure adhesive strength in thermally sprayed coatings. Very briefly on indentation, just video of the time. Let's say 5 more minutes. So indentation is something I've been working for some time now. So this is some of the fundamentals where you've got different type of probe, cylindrical punch or spherical or conical, or Vickers type or Knopf's type. So when you apply load, either material will deform, either way it will pile up or sink in. So there are different theory. The basic one is slip line, where you have got a maximum shear stress happening inside the material. The other one is hydrostatic pressure model, where you have got plastic deformation, a shell will be there, and then elastic deformation will happen. And as you apply load, the deformation will happen. Now, if you do instrumentation of these machines, the force using force and displacement transducer based on type of material or material you have manufactured, you can have different profile. You can have a profile coming from residual stress-free. You can compare with compressive, those material which has got high compressive stress, those with tensile stress. So the load displacement profile will shift a little bit in either way. So based on equal displacement approach, or you can based on equal load approach, you can work out the load difference or displacement difference, and then you can apply different equations to work out the residual stress when you are loading an object using either of those probes. So this is a summary of some of the 5 methods, patented methods. Means these equations they may be deploying in their instruments to measure the residual stress using indentation method. If you want to use a fracture model, so these are some of the fracture model. You can see Hertzian indentation is very known. Then median radial crack, median in loading, you can see this is what type of crack. When you unload, then you can have a lateral cracks which can pop up. And there are 2 different crack types, Palmquist and medium crack. And then during my research thesis, I was working on thermal spray. So thermal spray will not fracture the way these glass or ceramic material fails. In thermal spray coating, there are a lot of edge cracks and other smaller cracks, which you can't compare with the standard models. So that required different way of measuring cracks, where you can have a small measure those cracks using microscope or some imaging technique. So this zigzag length will be higher than the straight path. So if you use a straight path mechanism to measure crack length, you are actually undermining the fracture toughness values. So there are a lot of literature available. I have not presented here in much detail, but if you are interested, these are some of the original work or article. It will be good to cite them if you want to use nano indentation fracture to analyze the residual stress. Right, so last few slides, what next? In my opinion, I would say this residual stress analysis on thermal spray coating is a very interdisciplinary area. It requires partnership from material scientists to condition monitoring, to sensor application, to instrumentation, to control, thermal spray experts as well. So I would say physics, mechanics, materials, computer engineer, we all need to understand all these properties in coatings. The very little investigation which has been done in suspension or solution-based thermal spray coatings. Nanostructured powder has not been investigated much. Now, there are challenges if you want to measure strain in curved samples, spherical, cylindrical edges, or corners. In all those methods, I've shown the accuracy, the applicability, or the distribution. It still requires a lot of investigation. I believe that residual stress could become common testing protocols at coating both. However, we need to train future generation of spray users. I also see that things could go into different direction where a lot of digitization or digitalization could happen. For that to happen, I think application of sensing method and data-driven method and using HPC or access to HPC can help analyze some of these properties. So one of the work which we did long ago is based on acoustic emission sensor, where you can deploy AE sensor, one or more than one sensor. Here you can see sensor behind the substrate, and you can spray and then spray on the plate. So you can see here we have sprayed number of layers. It was extreme spraying. We did about 1 millimeter thick, and for each layer we build up, you can see the energy of acoustic emission is going up and up. And each of these points, each of these data points is actually average of hundreds of data points or hundreds of data files. However, if you analyze each of those files, you can see that it will have many additional signal features coming either from micro crack or a layer by layer crack, which could happen. So this is one of the experience we have. However, we think that a lot of additional sensing method can be deployed. You would know there are a number of techniques available. These are some of the techniques which is commercially available. They have deployed optical methods or pyrometry method to measure a number of things like temperature, velocity, plume, position, distribution, intensity, even weight. They can measure dimensions. Some of these techniques which are not, I would say, commercially available because these are still in R&D phase, but these can help measure cracking or number of particles sprayed as a coating builds up. There are many other sensing techniques beyond this list which can be deployed with the gun or spray system to monitor the spray process. So the last slide, where if you want to have a holistic approach, you can have an initial set of data, and each of these can be integrated with different sensing technique. There can be n number of sensors. So what you do with those data, you can fuse all these data, and based on the interpretation of the data, if you're looking for a strain management, you can build your models. You can modify your initial conditions, or in situ or off situ. So it requires multi-scale modeling, experimentally, numerically, to manage the strain in a structure like this. Right, so that's me. Thank you very much for your time.
Thank you so very much, Dr. Faisal. I'm simply mesmerized with that extensive coverage of various techniques that you covered. So let me invite now our audience, our community, to ask you any questions they may have, and then I'll ask you a final question at the end.
Thank you.
So if somebody has questions, please ask.
Faisal, if I can go first, because I need to get into another meeting right now. You said that liquid feedstock derived thermal spray coatings haven't been so well investigated. Why is that the case? You think there's no interest, or I would love to see something done there.
Well, I would say it requires further investigation. We did few work with Dr. Tanvir Hussain. I would say those are first few publications. But you see, these nanostructured material, it interacts, quenching happens for smaller materials. I think it requires more investigation, the crystal level. That is not known. We have done for larger powder particles.
Absolutely.
Larger substrate. What happens when you have got a thick coating using solution methods? There's not literature available. So I would say it requires more work.
Yeah, I mean, maybe we can take it offline, but that could be a very interesting area. Also, somewhat related is the kind of coatings that we have been doing recently, which are more of a hybrid variety where we use both powder and suspension at the same time for various things. Could be to introduce a solid lubricant or to incorporate graphene, could be whatever. And that's another kind of very unique system to investigate, I guess.
So you are making it much more complex. You have got a powder system,
exactly,
system. So the physics of the distribution or strain formation will be more complex. So it requires another level of modeling in it.
Yeah, because you have essentially two separate building blocks there, right? If you call a splat a building block, you have two entirely different building blocks which differ by almost 2 orders of magnitude, correct? So
yeah.
But yeah, let's take that separately. Sure.
Thank you.
Thank you, Dr. Joshi. Any other questions? So
Maybe then I can follow up with one more. Faisal, so if you need to do something like that, what would be a constraint? I mean, do you think we would always need time through an application from a neutron source or something like that to investigate? Or
yes, there are a number of sources we can apply for. Means Rutherford is one. We can look for ILL Grenoble. We can look for Australian source, and because we need these sources, or we can look for not only neutron, we can go for synchrotron. So for different approach, what we want to know, we can use different facilities.
Right. Okay.
there is one question coming from one of the members, Dr. Faisal, and the question is that you mentioned there's not much research done at the interface. What do you think is the reason for that, and what would be the ideal methodology to assess stress in the interface?
Interface means the main part is, as soon as the particle lands, the constriction, the constraint of expansion, because you are spraying another layer and you keep building the layer and layer. So it requires a different sensing method, or you spray first few particles and measure the strain, and then you do the spraying. So it is a time-consuming process. Or you can deploy some in situ method. You do first few particles only, and there are optical methods which can be deployed. So integration of these techniques, I would say, it requires interdisciplinary collaboration and resources to just pinpoint and work out a strain analysis for first few particles first and build up the model.
Great. Thank you, Dr. Faisal. So if nobody has question, I have three questions, Dr. Faisal. So my first question is, has anybody, except with the technique like neutron diffraction, looked particularly from non-destructive technique method into this?
Well, synchrotron is non-destructive. X-ray, these are non-destructive methods.
From a bulk method, not necessarily very highly localized method per se?
There are optical methods, but those are you don't do in a spray both condition. You take the sample off, then you analyze those things. So what I'm referring to at the end of my presentation is in situ during thermal spraying. That is where the innovation will be.
Okay, because at here in London South Bank, we have got an instrument which we are trying to look into methods on how can we augment some new areas for, let's say, non-destructive ways to assess subsurface damage, assess stress and other things using the so-called scanning acoustic microscope, which is looking a very promising technique to us. So
yeah, application of, I would say, some of the modern techniques, spectroscopy, and also optical methods, I would say in situ during spraying, I see more advantage.
Right. Something like gigahertz spectroscopy, for instance?
I don't know. I'm not expert in Raman spectroscopy, but I think that one technique can be really helpful if we can integrate during thermal spraying.
Sure. The other thing I wanted to ask, like when you showed these results, which are fascinating, of diametral compression versus neutron diffraction, and you said that there were differences, of course, which is fine. Is there any way to have a controlled sample to know this is what you expect from these two methods, and then benchmark these tests results that you showed against what would be the origins of the differences?
Yeah, so what we did, we used the disk standalone substrate only and put the strain gauge on both sides. And then we did the coded sample and did the same thing on both, putting a strain, and we analyzed. So I did not show in this presentation, but if you cite that paper, we have done analysis on a standalone substrate and coded substrate, and compared number of data under different loading condition, and compared with simulation, compared with neutron set data.
Great. I'll read that paper then. And final question, just out of my curiosity, being a modeler, is there a technique experimentally that you came across where we can look into the tensor rather than one single measurement at a point?
I think in optical methods, in some of those optical methods, they have used, but I have not done much investigation into that.
Okay. Thank you so much. Really appreciate your time and so comprehensive presentation. So any final questions?